is to define omega limit set as explicitly, okay? So the omega limit set corresponding to say initial data u naught is the collection of the equilibrium points psi such that for each psi you can always find a sequence of times that goes to infinity as n goes to infinity, and u evaluated at that time in long run converges to what you call the psi as n goes to infinity. So what is omega limit set? Omega limit set is a collection of the functions, okay, that are the functions of x only. So they are not the functions of what do you call time. So they are time independent functions, stationary functions, for which you can always find a sequence of what do you call a sequence of times that explodes, that goes to infinity, such that in long run the solution to the nonlinear evolution equation converges to what do you call this psi, okay, and obviously in h actually, okay, in h now. So this is what the definition of the omega limit set corresponding to the u naught is. Why it depends on u naught? Because the u depends on what do you call u naught actually, okay, u depends on u naught. There is another way to describe the omega limit set, okay. The other recipe to describe omega limit set is basically this. So I can, if I, for example, take a set, okay, I can also describe omega limit set corresponding to the initial data u naught as the union, okay, over the instants t greater than or equal to 0 of s of t u naught. And since s of t u naught can also be written as u of t, okay, you can also write this as u t bigger than or equal to 0 u of t, okay. But what are the explicit meaning of this set? This set means that it's the collection of s of t u naught, okay, it's a collection of s of t operated onto u naught for every time bigger than or equal to 0. So when I'm writing, this, I mean this actually, okay, I mean this. No, this is not omega limit set. This is just first the notation actually, that when I'm saying that union over t greater than or equal to 0 s of t u naught, what do I mean by that? I mean by that for every single instant t bigger than or equal to 0, calculate s of t u naught and put them in a set, so that would be this union. And equivalently, you can also write this as what do you call that this is the collection of u of t such that t bigger than or equal to 0 actually, okay. So all these four things represents the same thing, and there is a name for all these four descriptions, four recipes. So this name is that this is called the orbit of u is starting from u naught, okay. So this set or this set or this and this set, these all four sets means that it is basically an orbit of u that starts from what do you call u naught. You may also treat this as what do you call, I mean if you see this, you may also interpret this set and hence each of this set as a trajectory of the solution of the nonlinear evolution equation that starts from initial data u naught actually. So orbit is almost like a trajectory actually. Okay. Though there is a slight difference between both terms. Okay. But we're going to call this as an orbit. Alright, so we are happy with that. Now, what is omega limit set? One of the things that you can, for example, observe that if I have a set, say S of t u naught, such that t bigger than or equal to 0, and I have, say, another set that comprises of, say, S of t u naught such that t is bigger than or equal to 1, not from what do you call is that. So what are you going to say that which set is going to be the bigger set actually? So obviously this set is a bigger set actually. Okay, this set is a bigger set. Why it is a bigger set? Because this contains all information from 0, up to infinity about the trajectory of the solution, while this starts from what do you call 1. So this set contains this actually. So you can also say that if you give, you can also say that if you treat this set as a sequence that evolves over the time, then this sequence of sets is basically a decreasing sequence of the set actually, because that as you take t bigger than or equal to some number, the information shrinks actually. So you can also treat this as that this is this set, if you consider it over the time, you can treat this as that this is a sequence of sets, okay, that decreases over the time actually. Okay. Now it's time to define explicitly in another way what you call the omega limit set actually. So the omega limit set corresponding to say initial data, what you call u naught, can be treated as that take the orbit S of t, say u naught, okay, where the t is bigger than or equal to some instant s, and the closure of it, okay, and consider the intersection over of these closures over s bigger than or equal to 0. Okay. Now, as s increases, as s increases, this set is going to get small and small and small actually. Okay. As s gets bigger and bigger, this sequence of sets gets smaller and smaller and smaller. So you can treat omega limit set also as the intersection of what do you call intersection of the decreasing sequence of the closure of orbits actually. Okay, you take the orbits, consider their closure, and it's the intersection of decreasing sequence actually. So this is another way to say it. So one exercise for you, okay, to show is that this description 1 and description 2 of the omega limit set are equivalent to each other. So this is something that you have to do it for yourself, that 1 and 2 are equivalent to each other actually. Both definitions are equivalent. For most of the cases, we're going to use this definition, but at some instances we might also need this definition actually. Okay. What is the next? The next is whatever, now we define the omega limit set, say corresponding to one fixed initial data. What if now I have, say, a set A, okay, that is a subset of Hilbert space, and I would like to define what would be the meaning of the omega limit set for the collection of the initial data, not just one particular fixed initial data. The question is, what should be the meaning of it? The meaning of it is going to be, okay, the meaning of it is going to be what? I mean, if you are clever enough, you can really generalize this actually, so it's not a big deal. So the meaning of it is going to be that it is say the intersection of a decreasing sequence of sets, okay, which are basically the closures of the orbits, but now it is going to be the intersection of the closure of the union t bigger than or equal to s of, okay, so let's give this set name E of s actually, okay, so let's call this E of s. So omega of A is the intersection of a decreasing sequence of sets E of s, where what is E of s? E of s is basically the union of f of t operated onto the entire set A, where t is bigger than or equal to s and its closure actually. Okay, so the omega limit set is the intersection of a decreasing sequence of such sets actually. By the way, if you want to mean that what is st operated onto A explicitly, okay, so it is basically the s of t operated onto A, okay, where A is from A, okay, and t is bigger than or equal to 0. So this is what st of A actually means actually, that okay, let's operate s of t onto the every single element of A, and keep the things here for all t bigger than or equal to 0. So that if you have now a subset of the Banach space, then omega limit set for this calligraphic set A is the intersection of such sequence of sets actually, okay, such sequence of sets. But as I said, as you have this recipe to define omega of A, you can also define the omega of A in an equivalent manner, in the manner you have this description of omega of U naught actually. And remember, what is omega of U naught? We're gonna, in the terms of the nonlinear evolution equation, okay, for the nonlinear evolution equation, we're gonna see that it's the collection of the stationary solutions or equilibrium points of the nonlinear evolution equations to which U in long run converges actually. Okay, so if you want to know that which are those functions to which the solutions of the nonlinear evolution equation are going to converge, just go and investigate what we call the omega limit sets. The more explicit recipe to define omega of A is going to be that it's a collection of, say, phi's or maybe phi's for which you can find, say, a sequence that goes to infinity of numbers, real numbers that goes to infinity, and a sequence of functions in H actually. Okay, so a sequence of functions in H such that U f of t operated onto phi n, okay, converges to phi as n goes to infinity. Okay, so s of tn operated onto phi n converges to phi as n goes to infinity. So this is what is the explicit description of the omega limit set, but for a subset of the Hilbert space, the Banach space, that it's a collection of all such functions of x. Okay, it's a collection of all such stationary points for which you can find an exploding sequence of times and a sequence of functions in H, such that the trajectories of the function of the solution to your nonlinear evolution equation on that sequence that starts from the sequence phi n converges to what you call phi in long run, obviously in H. So this is what this means. And as you can prove that, you know, these two descriptions of omega limit sets are equivalent, you can also show that these two descriptions of the omega limit sets are also what do you call also equivalent actually. Okay, but I'm just leaving this for the exercise. So this description and the description that you have there, they both are equivalent descriptions of the omega limit sets actually. Okay, so a little bit of more definition. So here's a definition. So imagine I have a subset of H, the Hilbert space H. Then I'm going to call this subset, what do you call, positively invariant. Positively invariant if S of t operated onto the each element of x returns back an element in x actually. Okay, so S of t operated onto each element of x returns back an element in x. So I'm going to call this positively invariant. And I'm going to call this same x invariant, okay, invariant if S of t operated on to x is exactly equal to x actually. Exactly equal to x. Okay? So with these two basic definitions, now we are in position to prove some of the basic interesting results about the omega limit sets actually. And that will help us to explore some of the properties of the omega limit sets actually. Okay, so what is omega limit sets? Again, it's the collection of functions psi, which for nonlinear evolution equation we may interpret them as potential stationary solutions to which u can converge in long run actually. Okay, so it's a collection of functions of x for which you can find sequence such that u goes to converges to such functions in long run. Okay, so if you want to find the long term behavior of u, try to study the structure of the omega limit sets. Once you have both, you know, you have the long term behavior. We will specifically study, as I said, the omega limit sets for the gradient flows. So here are some of the basic properties of the omega limit sets in the terms of proposition. So as a lemma, so it says that suppose your f of t is C naught semigroup. So I have, say, S semigroup, so I'm not mentioning it, and I say that let A is a subset of what do you call H, a non-empty subset of H, then S of then the omega limit set for this set A, which can be singleton, in other words, which can be omega of u naught, and which can be, it can contain more than one element. The omega limit set for this A is positively invariant. First property is that it is positively invariant. So for a given subset of Banach space, the omega limit set of the set is positively invariant. And in order to show that, what I would like to show, that, okay, if you take an element from S of t operated onto omega of A, you will get back and operate S of t onto it, you will get back an element in omega of A actually. So this is what that I would like to show. Okay. So how can I show it? In order to show this, I need to pick an element from here and show that the same element would belong here. So let t is a non-negative instant, and say phi is an element. What do you call? Maybe let's fix, say phi is an element. Phi is an element S of t omega of A. Okay. Now, since the psi is an element in S of t omega of A, so what? So for sure there exists a phi in omega of A whose image is basically psi. Whose image is psi. By the way, in order to show that this psi is in omega of A, I need to find a sequence of times, remember? Sequence of time and a sequence of functions actually. Okay? Such that S of t evaluated at this sequence of time operated onto phi n converges to what do you call psi. The question is how to find such a sequence. The answer is, I don't know that for phi such a sequence exists or not, but since phi is here, so for the phi there exists a sequence actually. So as phi is in the omega limit set of A, so you can find a sequence of times and a sequence of functions such that S of Tn operated onto phi n converges to phi. Okay? Converges to phi. Question. What we should do next actually. The next thing that you can do is to exploit what do you call the continuity property of the semigroup actually. So we know that semigroup is the collection of linear bounded operators, so it must be a continuous map actually. And what we know, the basic fact about the continuous map, that it maps the convergent sequences onto the convergent sequence actually. So I have a sequence that converges to phi. So if I say apply S of t onto say S of Tn phi n, I'm gonna converge to what do you call S of t operated onto phi actually. Okay, so this is true by continuity of S of t. Now, what is S of t phi? Now, the S of t phi is basically what do you call psi. So I can say psi. So if I give these guys a name, say phi n of tilde, okay, then S of Tn phi n they are the elements in what do you call elements in A, okay, and S of t operated onto phi n of tilde converges to phi n. That is what follows from here, that S of t. Okay. No, I think I have to be a bit careful. I'm too quick. So you have this for sure actually. So you have this convergence for sure. But I need to show that S of Tn operated onto some functions should converge to the side. So I can apply the semigroup property. I can say that, okay, take your S of t and S of t and phi n, and since this S is a semigroup, so I can write this as S of t plus tn phi n, and I can say that this is same as S of tn plus t, so hence it's going to be S of tn, S of t operated onto phi n, and give these guys a name, say phi n of tilde. Okay? Hence you can say that S of tn phi n tilde, which is basically S of t operated onto S of tn phi n, converges to what do you call psi. Hence tn and phi n tilde are your required sequence such that S of tn phi n S of tn operated onto phi n. In other words, the trajectory. So what is the interpretation of it? The trajectories of the solution of your, say, nonlinear evolution equation starting from phi n converges to an equilibrium point, what do you call psi. And hence what does it show? That phi must be in omega limit set. So we picked an element from here and we showed that it belongs here, so this must be what do you call positively invariant actually. Okay? Positively invariant. What is next? What is next? The next is, or maybe corollary to this result is going to be that if you consider, say, the omega limit set for an initial condition, say u naught, this is also positively invariant. It's positively invariant. Okay? That's a quick corollary for this end. So in other words, that just take A to be the singleton u naught and apply this result and you have it. Okay? Now, the next result is an interesting result, an important one which we will later on use a lot. For this, I'm going to use some facts from topology, and I'm assuming that you know those facts. I'm not going to get into the proof of those basic topological facts actually. Okay? So here is the next important lemma. It says that suppose you have a subset of H, okay? Obviously, I want a non-empty subset of H. Then, and imagine I have an instant, say t naught bigger than or equal to 0, such that the trajectories of, say, S of t operated onto A for all t bigger than or equal to t naught, okay, are relatively compact. And this set is relatively compact. And if you remember, what do you mean by relatively compact? You know, a set is relatively compact if its closure is compact. That is, the closure of, say, union of f of t operated onto A, t bigger than or equal to, say, t naught, and its closure is compact. So you have two assumptions. Your A is non-empty, first thing, and say there is